Section 12.3, and this is about dot product. Turns out there are two ways to multiply the vectors, one of which happens to be called dot product, which is a scalar product. The other one is cross product, which is vector, and we will learn that in next section. So first, let's talk about dot product. The objective of this section is, what's the definition of the dot product? How do you find the angle between two non-zero vectors? What do they mean by orthogonal vectors? And what is a projection of a vector over a different vector? And we have two types of projections. One of them is scalar, the other one is vector projections. And then we will see some application problems. So let's get right to it. So the definition of dot product is if you have three vectors, either in 2D or 3D, the dot product, which is shown by U dot V, notice you make sure this dot is as visible as possible, is denoted by the sum of the product of what? Each corresponding X and Y and Z components from each vector. In other words, you multiply the X component of the U by X component of the V, Y component of the V, U by Y component of V, and so on and so forth, and add them up. At the end of the day, you get a scalar. Scalar means the answer is always a number. It could be zero, it could be negative, or it could be a positive number. So let's just try to find the dot product of these two vectors and see what happens. So we're trying to find the dot product of 0, 3, 4 by 10, 11, negative 2. So that would be 0 times 10 plus 3 times 11 plus 4 times negative 2. That would be 0 plus 33 minus 8, and that would be like 25. You all see that. So notice the answer came up as a number. Does it matter if I switch the order of what? Dot product. Turns out it doesn't matter. And so therefore, the idea is what? The dot product is commutative, meaning the order doesn't matter. Notice we still get 10 times 0, 11 times 3, and negative 2 times 4, which is 25. Is that right? So there you have it. In order to find the angle between two non-zero vectors, we have a theorem in the book which says the dot product of two vectors, besides being what defined this way, you can also compute it by the product of the magnitude of each vectors, namely what? A and B, times the cosine of the angle between them, where theta goes between 0 and pi. Okay, so what does that mean? That means if these are two non-zero vectors, namely A and B, so if you connect the terminal side of B to terminal side of A, that would be the vector called A minus B. Remember, that's how you find the difference between two vectors. So if you use the cosine formula from trigonometry, that would be like what? Opposite sine squared plus the square of the sum of the square of these minus twice of the product of the magnitude of these two sides times cosine. This is from trigonometry. So, but turns out the magnitude of what c squared is c dot c, which is the same as a minus b dot a minus b. And then lo and behold, that simplifies to this. So I guess the idea is this guy comes from the cosine formula from trigonometry classes. One other idea is orthogonal. Orthogonal is the same as perpendicular, but because you can have vectors in n dimension, so if the dimension of the space exceeds 3, so this doesn't make sense. I mean, how would you describe two vectors to be perpendicular in, let's say, in fifth dimension? You don't even know how they look like because we don't have any geometric interpretation for them, meaning there are no pictures. Well, it turns out from this formula, if theta happens to be 90 degrees, cosine of 90 is what? 0. So A dot B turns out to be what? Equal to 0. So what does that mean? That means this is a way to check and see if two vectors are orthogonal, which is the same as perpendicular to each other. All you have to do, check and see their dot product is 0, the number, yes? Because if theta is 90 degrees, cosine of 90 is 0, so this whole expression on the right side of this formula from this theorem becomes 0, so that what results in A dot B equals 0. So now let's find the angle between what? These two sides of this triangle. So remember, you can't see these axes, so they are hidden, so that's what the dotted lines are. So what is theta? Well, first of all, we have the initial and the terminal points of these two vectors. So let's express them in terms of vectors. So that would be like terminal minus initial. So that would be like what? -1, 1, 0. Terminal minus initial. 0 minus 1, 1 minus 0, 0 minus 0. So PR is terminal minus initial, 0 minus 1, 0 minus 0, 2 minus 0 is 2. Now I'm going to use the formula P, what? Q dotted with PR equals magnitude of PQ times magnitude of PR times cosine of the angle between them, which theta goes between 0 and pi, correct? So now what we got is what? -110 dotted with -102, and the magnitude of PQ is the square root of 1 squared plus 1 squared plus 0 squared, which is square root of 2. Magnitude of PR is 1 squared plus 0 squared plus 2 squared, which is 5, cosine of theta. But remember, the dot product is a number, so -1 times -1 is +1. 1 times 0 is 0. 0 times 2 is 0. And square root of 2 times the square root of 5 is square root of 10. So you get square root of 10 cosine theta. So cosine theta is 1 over square root of 10. So theta is cosine inverse of what? 1 over square root of 10, which is about 71.6 degrees. So that would be the angle between these two vectors, which we found it by the alternative formula for the dot product. Remember what the word projection is. Projection means shadow. Is that right? So that means shadow. Okay. So what would be the shadow of one vector over a different vector? And assumption is none of these guys are a zero vector. Well, when you talk about shadow, first of all, shadow has length, okay, and it has a direction. If you're interested in what? Finding the length of the shadow of A over B, vector B, that's called scalar projection, which is denoted by COM. That means the component of A onto B. So this is like the notation for a scalar projection of one vector onto, the word is onto, a different vector. On the other hand, if you're interested in the what? Vector itself, the shadow itself, you know, the direction, that's called a vector projection of A onto what? B, and it's denoted by PROJ projection, A onto B. Remember, these notations, they kind of go like this. COMPA and then subscript B. Up here for vector projection, you kind of go PROJ A subscript B. That means the vector projection of A onto B. This means the what? Scalar projection of A onto B. So this guy is the length of what? The shadow. Is that right? Of A onto B. And this guy is the what? The vector, you know, the shadow itself, the vector. So it means what? The shadow itself, so it's about directions, correct? Or direction. So how do you do this? Okay, so if you drop a perpendicular line from A to onto B, so this guy is at 90 degrees, so the length here is equal to what? So the length, which is scalar projection of A to B, is equal to magnitude of A, which is what? Hypotenuse, times the cosine of the adjacent angle, correct? But now the idea is, suppose I don't know theta, how would I then convert this to a dot product? So if you give a denominator of 1 to this, and then you multiply top and bottom by the magnitude of B, that doesn't change anything. But if you multiply the tops, you get magnitude of A times magnitude of B times the cosine of the angle theta over magnitude of B. But guess what? The top is precisely equal to A dot B. Remember the theorem, A dot B, A dot, the dot product of A and B is magnitude of A times magnitude of B times cosine of the theta. And that's what this guy is. So I can now tell what? The scalar projection of A onto B is A dot B over the magnitude of B. So you want to make a note of this formula, which is a number. Is that right? So this guy is a number. So this is like the length of the shadow. If you shine a light here and you see the shadow of vector A onto vector B. Well, what about the shadow itself, which is a vector? Well, if you just take the what, so this is projection, the vector projection of A to B, A onto B. Well, you got its length, which is what? A dot B over magnitude of B. All you have to do is what? Multiply this guy by a unit vector along vector B. So that way you can give it direction to this what? Scalar. How do you find a unit vector along any vector? You take the vector divided by its what? Magnitude. So what are you saying? I'm saying the answer is what? A dot B over magnitude of B squared B, vector B. There you go. So there you have it. That would be the vector projection of A onto B. So let's follow this formula and see how would you go about finding the scalar projection of A onto B and vector projection of A onto B. Remember, this guy is a scalar, is a number, but this guy gives you a what? A vector. Is that right? So how do you do this if you follow the formula here? That would be like what? A dot B over magnitude of B, correct? Based on the formula. So if this guy was V and W, then it would be V dot W over magnitude of W. All right then, so let's do this. So if you take the dot product, that's 2 times 1 is 2. Negative 3 times 6 is negative 18. 1 times -2 is -2. And this is magnitude of b, which is the square root of 1 plus what? 36 plus 4. That will be 1 squared plus 6 squared plus 4 squared. Take the square root. The 2's cancel, so you get what? -18, is that right? Over square root of, what is this? 41. Notice it's a number, yes? And to change that to a vector notation, so what we do is what? Take this, which is a dot b over magnitude of b, correct? And then multiply it by a unit vector along b. So that would be like what? B divided by its magnitude, so that would be b, this guy will be squared. So the answer is a dot b, which is what? -18 over this guy, magnitude of b squared, so that's 41, correct? Times the vector b, which is 1, 6, -2. So that would be like -18 over 41, negative, what, 108, is it? 41, and positive 36 over 41. Is that right? So remember, this guy comes up to a vector, whereas this guy is a number, correct? So there you have it. So now let's take a look at what? Some applications. One of the applications we like to work with is the work, which is defined as force times displacement. So here's the deal. You have a sled here, which is pulled by a rope, which has 30 pounds of force, okay? So that's the magnitude of the force, not the force itself. And it's constant. So this rope is pulled at a constant force of 30 pounds. And the angle which this force makes with a horizontal level is 40 degrees. And we're trying to what? Move the sled like 80 feet from where it is. From starting to end, it's 80 feet. Can you find the work done by what? Force F onto this sled. Okay, so remember the formula is work is equal to force times displacement, placement, correct? So work is shown by W, and this would be like what? F dot D, correct? That's the dot product. However, I do know the angle, so I'm going to use the alternative formula, which is the magnitude of F times magnitude of D times cosine of the angle between force and the what? And the horizontal level. So in this case, magnitude of force was given as 30 pounds. Distance displacement was 80. Cosine of what? 40 degrees. So we have the answer, correct? So what would be the final answer? So the final answer would be something like 1,839, and the unit is foot-pound. It's not foot per pound, it's foot-pound, because the formula for work is force times distance. Force is pounds, distance is feet, so it's foot-pound. All right. Sometimes instead of magnitude of the force, you have the direction of the force. And let's say this force moves a particle from point A to point B, like in this case from point P to Q. Find the work required. Once again, the formula is work is equal to what? Force times displacement, is that right? Which is the same as F dot D. We do know F, which is given to us as what? 345. Remember, this is not the magnitude. This is the vector force. Force in terms of vector. Dotted with displacement. Displacement is like what? We're going from point P to Q. So that would be like what? Knowing the initial and the terminal points of the what? Vector. So you know how to convert that to what? Vector. So terminal minus initial. So that would be 4 minus 2 is 2. 6 minus 1 is 5. 2 minus 0 is 2. There it is. So that's 2, 5, 2. So now we take the dot product of these guys. So that would be like 3 times 2 is 6, 4 times 5 is 20, 5 times 2 is 10, so that would be 36, and that would be like units of work. Remember, if the force is in what? Pound, the distance is what? Feet, so that would be foot-pound. If the force is in newtons, and what? Distance is meters, then the work would, the unit for work will be joules, all right? So there you have it. So what are other applications of what? Dot product, or I should say the applications of the projections? Well, you will see these applications in section 12.5. One of them is using what? The projection idea to find the distance between a point and a plane. And the other one is finding the volume of a rectangular box. Remember, when I say finding the rectangular box, I mean a box which has been smashed like this. So we cannot use length times width times height straight up from the diagram, because the box has, someone has stepped on the box, so the height is no longer perpendicular. So we need to use the idea of projection to find the volume here. And that's coming up in 12.5. All right, some properties of dot product. Notice the order when you take the dot product, it's irrelevant, so the order doesn't matter. So we call this commutative property. If you take what? The vector and what? Dot it by itself, you get magnitude of that vector squared. How is that? Because if A is equal to, let's say, A1, A2, A3, and I take A and dot it with itself, A1, A2, A3, dot it with A1, A2, A3, I get A1 squared plus what? A2 squared plus A3 squared. But that's exactly the magnitude of the what? A squared. If you take a what? Zero vector and dot it with a vector, you get zero the number, not a vector. Be careful. This guy is zero vector. Is that right? And this guy, the answer comes up as a number because the dot product is a scalar. This is distributive law, so A dotted with B plus C is A dotted B plus A dotted C. Special dot products for standard unit vectors. I dotted with I is 1 because I is what? A unit vector along the positive x-axis. You take the dot product of I and I, you get 1. But if you take the dot product of the I and j, you get 0. IK 0, J dot J1, K dot K1. So if you take the dot product of the I by itself, J by itself, K by itself, you get 1. Any other case, you get 0. Remember what I was. So I was a unit vector along the what? X-axis, J was a unit vector along the Y-axis, and K was a unit vector along the what? Z-axis. And that pretty much does it for this section. Thank you.